Yo, everybody, what's up? Welcome on this awesome Saturday. Yeah, it's Saturday. We are here in San Francisco. It's nice and cloudy, as you can tell. We're heading to escape out of the cloudy San Francisco, head to Bora Bora in the Pacific Southwest. And from Bora Bora, we'll probably, to be exact, we're heading from Bora Bora to Tahiti. And then we're headed from San Francisco to Bora Bora. And then tomorrow probably fly a turboprop from Bora Bora, well, Tahiti to Bora Bora. Um, as you can tell, this is our, the flight data is back, which is great. And what we're going to do is I'm actually going to pull up the charts right now. And I'm also going to make sure that we have our active schedule. Good. So, welcome back. Cool. We're right now at the airport, as it shows. I actually load up that flight on the chart here, and let me give you the brief of what the weather looks like too. And then once we're ready, we'll start up the plane. Okay, I'm gonna load that right there. The import flight from San Francisco to yes. Alright, so we won't be passing the actual lakes, actual island of Hawaii, but we'll see itself. So first we're gonna first things first, we are actually going to set up something itself. The batteries are off. All these lights are going to shut off in about 5 seconds. Like preparation, fuel manager, gonna look like. Yes, everything just died out on us. Sorry about that. That's what that means. So, okay, let's go. Yellow manager. Let's hope that our first nine passengers. 85 85.9 right there. That's what. So, right there. That one just down to that. Here, that's in. Get that. Like that. Well, now, it's a checklist page. Safety. Parks are said. Yep, everything here we don't care about. Yeah, we can skip that. Technical log, pre-check that gun power's on, battery power's on, shit. Oxygen panels, game has the heaters. Check that. But first, we're going to turn on the iris, which is like the iris, but well, more. So we're going to do it online here, on once, or twice, 3 times. Area irises are set. Air data. Here's right here. 1, 2. You see it cooking. It's looking. Everything here. Now if I can go on. Drain master heaters. Let's go 1, 2, 1, 2. Here. CB is all of these guys. Oxygen set, TV windows. For now, look at the windows over here. Alright. Light control inverter. These are light control inverter. All on anti-system. So we got flight control, anti-system, IRS, radio. Actually, first, we don't have a computer, so we're first gonna check on the weather. So if you look at San Fransico, it's 298. So if you look at our weather, the line is good. Right. No, no, right. So Grammy 3. Initial climb is 3,000 feet. 1, 2, and we're just going to take it the fairway all the way through 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. Look at that. Let's look at okay. Okay. That radio and I is set. So we're just going to be taking you out. So, and as the instrument said, altimeter. So here's our altimeter right here. So the altimeter is right here. So let me show you the altimeters. So if you look at the weather, the altimeter station is a mark. Just there. Okay, yeah. Altimeter, autopilot panel right here. So, yeah. Here's how the brakes are set. Nav lights is educated. Here, here. Let me look at that. Right. Right. Alright, here's all this stuff back here. This is the fun stuff. Your ground hook decks. Yellow, yellow, off, off, good. Here's auto, 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 auto. Enter your legs. Shut. Secondary. We're taking off in 3 here. So that's gonna be auto, 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 auto. Batteries are off. Check. INS. They're not right aligned. But they're not aligned for depth. They're fine. So north. So first, north. 3, north, 36139. Yeah, we are different plants. That's one of them. Actually, both of them. And both of them are, yeah. So, today we're not going to actually head to the enemy portal, we're going to head to the east first for a first. And that's what we're looking for. And I think now we're going to do like Monday. 5, 4, 4. Transition power and my chart. On a chart that I have. Alright, so take it to big 5. North. South. 5. Yep. Yep. 5. I'm so glad I caught that. Okay, actually that was south. 5, 7, 4, 0, 4, west, 1, 4, 3, 3, south, 2, 3, west, 1, 9, south, 1, 7. Hey, one of the rival waypoints is Moana. 2, 5, 3, west, 1, 4, 9, 0, 7. Come on. South. 1, west, 1, 4, 5, south. 1, 7, 4, 9, west, 4, there we go. Alright, we've got a pipeline cloud. INS is aligned. And actually, let me show you what our pipeline is. So, we're going to start off here in San Francisco. Go from San Francisco to the Pacific. Right there, from Pacific. We're headed all the way down. There's Hawaii, all the way down south. Going down south. Yeah, like that. Here, from Mach, we're going down to Soki, take us to Mana to Tahiti, over to Hawaii. That's our plan for today. So, that, so from that, we're gonna actually get started. Start here. INS set IS was we started. So briefing, yes, briefing. Then, oh, and we're taking up alright, to 8, so we should probably set up everything for the running stuff. The INS clock is set, fuel, load is checked, set, take off data set, take off data, product, all that. I take off. And actually, sure. If problem not fuel or and now we're ditching somewhere. And if I want to 95.3. Alright, so let's start our how to like that. Actually, yeah. There, set. Alright, clear as hard. And we're gonna turn off. Doors here. The aircraft doors come. Doors. And everything is ready to go. First, carefully, real cool. And our autopilots have set up. So, I'll let take some picture. Yep. 246. Okay. Video towards the available. Available actually, alright. Cool. So that was fun to hear. Actually, okay, cool. You can hear everything I say. Okay, now, what's next? Let's start. So we always start off with the import. 3 and 2. Yeah, so we're just gonna 3. Oh, wait. All of our fuel pumps going on. There we go. Now we're ready to start. Okay. Engine 3. Start. There we go. That's what we'll see. And if you want to hear the engine. And I might not hear it much, but it's going to get loud fast. Like, just like engine 4, engine 3. And let's actually start our push.
Hey, Captain, let me know where you want this thing.
There's that engine.
Great news, Captain. Your tow's coming.
Thank you. Engine 2, we like it.
Alright, looks like the doors and hatches are closed and we're ready to connect. Welcome aboard, Captain. Toes connected, bypass pens inserted. Go and kill the parking brake when you're ready to go.
Alright, thank you. Press start. Now. Custom box open. 2, 2, cool. Before push. It does. Ground bypass is online. Ag electrical access needs to be closed. Make sure share caliper to work on. Water heaters come on. There we go.
Here comes the pushback.
Engine number 4. And let's get the flicker. Look at it, run, click on it. Nice. Watch out.
Just about done here. Go ahead and set your parking brake. And we're disconnecting the tow. Give me just a moment.
And you have to kill that engine. Alright, yeah. The one stabilized. Custody valves come off. Now we're less hydraulics.
And we're disconnected. Signal and pin on the left. Take it easy and have a safe flight.
Thank you. Just want to make sure that my nose turning out working. Okay, yeah, that worked. Alright, go to your attention. So here's okay. Come on. The plan first schedule is flyover. Alright, here's the fun part. Switch here. Have to be down. Switch here. Have to be back. Open windows here. And check the flags. Alright, let's go. And we'll start testing. Let's get cancel out the first just in case. And let's get out of here. Alright, CG fuel. Alright guys, he's ready to run out of here. Out of here. Look at that long bird. I just saw you guys' comment. Gaming is that's playing 11 and just Bora Bora. You didn't know it. So X as in letters, playing as in playing itself, and then number 11. So remember, we're going to be taking off my screen, right? And we're going to So Fire set, brake temps clear, and we're good here. And I like to come on. Alright, let's do it. Hello, Concorde. Alright guys, don't forget we're going to be flying Mach 2 today. Like the speed down. Down. We're probably doing like a 4.5 hour flight. Here we go. Concorde, let's go. Let's do this. Look at that engine. That. Alright, he's ready to rock out here. Concorde style. Nicely done on cinema. Okay.
3, 2, 1, now.
Wait. Alright. You guys gotta keep a follow for of this. There's something on. actually 85. And look at that, people. Look at that speed. 30 on the speed. Let's go. Let's see about it. Ladies and gentlemen, the Concorde. Alright. Let's here we are. Yeah. And we're gonna go now. Alright, check this. Now I check when you get check. Off. Off. I just did check on it today. And checked. Look at that, we're perfectly on track. Alright, so next altitude is 28,000. These are to fly. We are let's go. Up. Such a heavy bird. It's good to just sometimes just see land. Another 20 sheets of the shape. Alright, let's see how they do. How they do. Pretty good.
10,000 feet.
Yeah, it's already at 2,000 feet. Let's see. I'm actually doing pretty good. How are you guys doing today? Um, we're gonna just get my food and up. Load and not so well. And the thing on. But I'm actually pretty good. Uh,
350 knots.
I wrote out a bit like 10 minutes before the stream. So I went out of bed, put myself up, and then got on here and started streaming. So pretty good. Although soon enough I might actually have to get some breakfast plus lunch. I haven't gotten it just yet. So maybe I can do that during the stream. And it's fun just because alright. Alright, man, like, you don't think I got it. And we're gonna turn off the bus signs off once we get to 3 minutes. Look at that. Or 2000 feet. Alright, since we passed the speed and are just getting liquid cloud and the sonic cruise, I'm gonna start some music and lower the volume or still hear it. Ish. Yeah, that works. And here, and that actually works. Cool. Let's get some audio in here first. Alright. Where's the audio? I actually want to see if that works. Okay, cool. It does work. Yeah. I thought that was an issue on my side. But first, it's actually due to the flood. Just a tad so you don't blow off your eardrums. Let's go. Better. I haven't passed transition altitude, so transition altitude is 292. 292. I'm gonna try that. Another altitude. Yeah. Let me adjust my. Okay. Ooh, that is so much better. Whew. Actually, oh, that's not right. That one I want. Monitor that. Oh. So does that work? Oh, that does work. Okay, cool. That does seem to work just a tad. Why must I? Cool. That seems to work just a tad. On measure install. And we are close to cruising altitude. Well, not really. 260. Yeah. 260. 280. Let's get to 80. We are going to start our out here. That'll be about 5 minutes. 5 minutes from now until we get onto the, I don't know, but slowly and steady. Weird. Huh. Man, later. First, flight data up top might not be as accurate as I'm hoping, but it'll get the job done. Great. I got it on. I'm gonna head out. Alright, and I'm gonna transition over. Once we get to Mach 2 and everything, well, I'll go get some dinner, come back, brunch, come back, and we'll see what's happening after that. For now, we're just gonna look at this ocean. Literally nothing but ocean out here. Actually, no one's actually here. I have to just switch screen over for a second. Hello. Can I get my audio louder? No, it's not. Hello, hello. Okay, how's that? Bit better. Whoa. Okay, yeah, that is, well, that is so much better. Okay, this one, nope. Alright. Just after my microphone. This. I'll stream back on. That's right, today is 280. Nope, we're 200 feet off. And we're close to waypoint 2. Helps. What 8,000 feet, there we are. About 9 seconds from now. Actually, I was really like, oh, yeah. Like 30%. There it is. That's what I'm on. The audio. Cool. That works. There's turn. Let's see. Wow. There's standard. Okay. Views. There it is. There we go. Alright, we're ready for Mach 2. Let's do this. 60,000 feet. Set. Next climb. Converter off. Alright guys, so here's the next step in setting up our Mach 2. Turn that off. Wait a sec. Ready? Alright. Ready. Go forward first. Pull left burn. Look at that. Ladies and gentlemen, we're going twice. Let's take you across. Ladies and gentlemen, welcome to Mach 1. No bumps, no pains. All smooth. Bumps, no pains. Mach 2. And Mach 1. Passing 30,000 feet now. Just want to make sure. $35, 30.6, so yeah, that is clear. Cool. This works. Wait, what? Cool. Okay, on audio. Cool. There we go. Cool, that works. And we're coming up to 40,000 feet. Alright, so, let me show you something, guys. So, right here, these are little... There's some right here. Oh, okay. These ramps right here, those help airflow. Since Mach 2, birds flying twice the speed of sound, there's gonna be a lot of wind passing through, making it hard to get air to the engines, causing them to surge or fire, or equivalent. So these ramps help us regulate the air outside, and I can actually show you what that looks like. Got aircraft. Cool. That's your key. Okay. I want to show you guys back. Never mind, can't show you. There's a way I can show you. I don't know. Okay, actually, yes there is. Engines. These are the ramps that I want to show you. Those are right there. The inflow intake valves are all normal. Cool. Once I turn off the reheat, it's gonna do everything else for me, and we'll be good from here. I'm gonna turn off the reheat around Mach 1.7. Or Mach 1.8. Or actually right now. Reheat's coming off. And we're good here. Actually, do something here. Let's stop the audio for now. Second, well, Concorde, 5. Mach 2, well, Mach 1.8. Okay. Whoa. That was a bit loud. Sorry about that. I'll try again. That was cool. By the way, those sounds you were hearing are actually the sonic boom. Since playing is 1 and press speed sound, there are 2 points on playing. Here and here. Back. Basically, the plane is creating a sonic boom around the entire plane. Let me show you what a sonic boom looks like, and let me show you why it's doing that. Alright, so, if you have ever seen a fighter jet take off and fly twice the speed of sound, you'll notice there is a cloud shape right behind the cloud. That is sonic boom. So, I'm going to show you what. Let me get the back. What is a sonic boom? A sonic boom is a thunder-like noise a person on the ground hears when an aircraft or other type of aerospace vehicles fly overhead faster than the speed of sound or supersonic aircraft fluid to supersonic objects. So, show that. Okay. This show. Alright, now, how can, so, that's what a sonic boom. Now, let me show you what a sonic boom on Concorde looks like. Just, that's, okay. Here, I just use boom. Cool. So, 2 seconds here. 15 seconds, there it is. Cool. So, that's a sonic boom. It's, the plane is literally flying twice the speed of sound. I kind of wish that X-Plane could represent sonic booms. Well, they can, but you can't really see them on Concorde. But this is what a sonic boom would look like. So it's like thunder, not that really fast, well, really loud. So Yeah, that's the song. Oh, gee. Oh, so relaxed. But feeling high something. But you can spaghetti. Love that name. Love spaghetti and love that name. Hello, welcome to the stream. Uh, we're flying Concorde to Bora Bora. The world's, well, our Concorde. And, thanks for the 2 likes. And don't forget, guys, to subscribe to the channel. Guys, yeah, or you guys want to. But, yeah. Welcome to the channel. Sure. Happy, ladies and gentlemen, looks like we've already reached Mach 2. No bumps, no bangs, Concorde, twice the speed zone. 165 minutes, or 165 minutes until, which is, what, like 3 hours, give or take, until we arrive into Bora Bora. I'll be back for food. Thanks for watching, guys, and stick around. We'll be arriving like 3.5 hours, give or take. I'll play some music for us and show. I just realized you guys can't see any. Perfect. What the heck is that? Alright. Let's listen to music. I'll be back. Yo, 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 we are back. Let's see, what are we dealing with? I'm sorry for stepping away for so long. I had to deal with these, but we are here now. Let's look at some stuff. Let's go to map. Right now, let's see what we're dealing with. Um, okay, so we have about an hour and a half until we land, and we've already passed Hawaii. So, yeah, we're close. How? And it's 4 hours, 4.5 hours. Okay. So we only have like an hour and a half to go. Alright guys, we have an hour and a half to go. We should probably start planning our descent soon. So, not bad considering how we do. Down speed, as they're cruising right now. We need to be down. How fast? A lot of supply. We are currently halfway. Give or take. Maybe 3,000 feet. Right. Yeah, 3,000 feet. That altitude. This should work. $175 nautical miles until a truck drop, but that's probably nope. That's what I mean. So do some calculations here.
60,000 feet.
There's enough. Cool. So 3-1. Yeah, okay. So 135, 168. Over 5 plus 96 plus 15. Minus 7. Okay, so we want to start around 14 nautical miles from Mississauga. Yeah. That's the plan, right? Actually, uh, alright, nautical miles, you get 3,000 feet, times that by 3, divide that by 1,000, 171 nautical miles, minus 7, minus 6, minus 10, minus 7, minus 30, minus 28, 80, so now we can check the X minus 8, 46 nautical miles from Sakami, which makes sense. Okay, cool. Flight. Stanford. Airhead transition. Don't mind those two blinking lights. Okay. Uh, I wanna be alive. But I promise 2 hours, 3 hours. Alright. Have you guys been? Just. Yes, it's gonna be like an hour and a half till top and drop. Well, hour till drop. But, you know, it's gonna be a while. Uh, yeah. I kinda forgot how many passengers there are. So, you know. Okay, so these should be a little bit more fun, shouldn't we? To watch videos. Huh. Let's see, what are the rules about copyright? Uh, since we're in aviation for now, let's see if Hey, I don't know if I'm gonna get copyrighted for this, but I want to try something here. We think we don't need that right now, actually. We're gonna try something here. YouTube, I don't know if this sort of copyright, but I'll try this right now. Do display capture. Okay, okay. Uh, wait, no. Oh, that. I want. Just give me a second here. That's not cool. Just another. Wait, nope. Yeah. Uh. uh there we go. Cool. Alright, now display capture here. Sort of works. What if I. There we go. I'm just gonna try something here. Hopefully I don't get copyrighted for this. But if I do, oh well. Alright. Good. There it is.
This episode of Real Engineering is brought to you by the Curiosity Stream and Nebula Bundle Deal. Watch the latest episode of our new series, The Battle of Britain, on Nebula for just $14.79 a year. In 1969, a pioneering vision of the future made its debut to the public.
In a few years' time, the sight of Concordes on international airfields all over the world will be commonplace if all goes well. Then there'll be 130 passengers on board. Flying times will have been cut by half. London to New York from 7 hours 40 minutes to 3 hours 25 minutes.
The juxtaposition between this dated footage and the futuristic plane is strange. It's hard to believe passengers 40 years ago, in a time when color TV was a luxury, were flying across the Atlantic at the speed of sound. The Concorde was well ahead of its time, an anomaly in the history of commercial travel, a byproduct of misguided government funding, a joint venture between Britain's BAC and France's Aerospatiale, and its development funded entirely by the British and French governments to the tune of $2.8 billion. The Concorde's legacy is marred by its commercial failure, but this engineering marvel was a triumph of ingenuity. Nothing remotely close to it had flown before, and nothing like it has flown since, turning what had been a military-only technology into a luxury flying experience required innovative thinking. This is the insane engineering of the Concorde. The engineers of the Concorde had several unique challenges. Developing a supersonic plane is difficult enough with military design requirements, but developing a supersonic plane that would satisfy the wealthy customers it intended to serve is an entirely different ballgame. Aerial refueling makes fuel efficiency a secondary concern for the military. The comfort of the plane's passengers is an afterthought at best, and the price tag attached to these often limited-run specialty planes is beyond the budget of a commercial airline. Those needs are reflected in the Concorde's unique design. A sleek exterior hiding powerful engines. Engines developed from the iconic British warplane, the Avro Vulcan. Fuel efficiency and supersonic flight are two opposing ideas. But these engines, the Rolls-Royce Olympus 593, when flying at Mach 2, were the most efficient engines ever created. These engines, when introduced for the Avro Vulcan, were capable of generating just 49 kilonewtons of thrust. But over the course of their adaptation for use in the Concorde, increased in thrust by over triple to a whopping 169 kilonewtons. 20% of this thrust increase was provided by newly fitted afterburners, a technology typically reserved for military planes. Afterburners work by injecting fuel directly into the superheated and high-pressure exhaust of the turbine section. Despite this air's journey taking it through the combustion chamber, only half of the oxygen in the air is consumed, leaving untapped energy in the exhaust of these engines. To capture this energy, fuel can be injected directly into the exhaust of the turbines and ignited, basically acting like a rocket stage of the engine, causing further expansion and acceleration of the exhaust through the exhaust nozzle. However, this system is useless without a controllable nozzle. Typical airliner engines have a fixed nozzle, because these aircraft are expected to be efficient at a relatively low range of subsonic speeds. But the Concorde, with its massive range of speeds, needs not one, but two controllable nozzles to adequately control the engine's power. The primary nozzle connects directly to the jet pipe's exit and consists of petal-like structures that can close or open to vary the diameter and therefore the area of the jet's exit. When the afterburner, or reheat as the British engineers called it, was ignited, it caused a massive increase in pressure at the engine's exhaust. This increase in pressure could cause choked flow in the engine, where high-pressure zones ahead of
As I'm in the midst of applying for residency right now, wish me luck, Grammarly has again been a lifesaver with my application and helping me write my personal statement and CV. Grammarly is your digital writing assistant. It's an all-in-one tool that improves your productivity, triple checks your work, and saves you time when working on multiple assignments. Even the free features are incredible. You can set your own writing goals, track your word counts, and even find new words to replace your overused ones using the synonym feature. I personally love using Grammarly.
lower pressure zones will prevent air from flowing through the engine correctly. To prevent that, the primary nozzle opens wider when the afterburner is active to decrease pressure and ensure the mass flow rate through the engine is unchanged. However, at times, we do want to affect the flow upstream of the nozzle. The Olympus 593 was one of the world's first, predated only by the Pratt & Whitney J57 engine by just a couple of months. Two-spool means the engine contained two compressor sections driven by two turbine sections, each acting on their own concentric drive shafts, allowing the two sections to operate at different rotational speeds. When the primary nozzle was actuated, the varying nozzle pressure caused the low-pressure spool to either spin faster or slower. thus providing control of the engine to ensure it can perform at its optimum speed across its wide speed range. The secondary nozzle function is just as complex. The eyelet doors look like some kind of steampunk blast shield, and for good reason. The force these secondary nozzles had to endure influenced their appearance, withstanding huge forces at both supersonic and subsonic speeds, and they could even close completely on landing to function as reverse thrusters. By actuating these nozzles, the plane could carefully manipulate the exhaust velocity and thus maximize thrust because together the pair acted as a controllable converging diverging nozzle. Converging diverging nozzles are typically used in rockets to accelerate the combustion products to their optimum speed and pressure. The opposite shapes are needed because air acts completely differently at subsonic and supersonic speeds. For example, when subsonic air travels through a converging duct, it speeds up as the cross-sectional area decreases until some critical area, which is referred to as the throat. This is where Mach 1 would be reached. At this point, no further acceleration of air can occur as the flow is choked. Now, as you would expect, if that same subsonic airflow went through a diverging duct, the air slows down as the duct area increases. This is Bernoulli's principle at play. The bizarre thing is, the exact opposite occurs when air travels at supersonic speeds. A converging duct will result in a decrease in velocity, and a diverging duct will result in an acceleration. So, in order to maximize the acceleration of our exhaust gases, we want to pass our subsonic air from the engine first through a converging nozzle, the primary nozzle, until it reaches Mach 1 at the throat. Then we want it to pass through a diverging duct, the secondary nozzle, at supersonic speeds so it can continue to accelerate. These paired nozzles allow the Concorde to carefully optimize the nozzle profile for different flight conditions, a marvelous piece of engineering. The same principles were used for the inlet. No engine can operate with supersonic flow. The shockwaves that would form inside the engine would cause all kinds of chaos. So the Olympus 593 needed some way to decelerate the supersonic air entering its unique square inlets. These squared inlets were designed to simplify the complicated task of creating nice laminar subsonic flow for the engine's compressors. Inside were a series of ramps and doors that could open and close depending on the flight regime the intake was encountering. At takeoff, the engines required all the air they could get to accelerate the plane enough to get those cumbersome delta wings to generate enough lift to take off. To funnel as much air as possible into the engine, the two variable ramps were retracted into their closed position. A spill door in front of the engine intake was held open to allow additional airflow into the engine, while two bypass doors, which controlled the air around the cooling passage around the engine, were also closed. The afterburners were also active during takeoff, but soon after, the Concorde was required to enter a noise abatement stage of flight, where the afterburners were turned off and power was reduced as the plane climbed. At this point, the bypass doors open to allow for cooling air to travel along the outside of the engine. As speed increases, the primary and secondary nozzles adapt, gradually beginning to form the ideal converging diverging nozzle for supersonic cruise. Parallel to these changes in the nozzles, the inlet ramps actuate to create a converging inlet that slows down and compresses the supersonic air entering the engine. The fuel consumption of supersonic flight is massive, but that is primarily driven by aerodynamic drag, not thermal efficiency. This supersonic air being rammed and compressed into the engines helped the engine immensely in achieving its high thermal efficiency. Thermal efficiency.
Any creators that are looking to level up their storytelling and their
Don't need to see that. Alright. Channels, that. Check. There you go.
Largely to
Alright. That works.
determined by the pressure ratio achieved by the engine. That is the ratio of pressure between the inlet of the engine and the outlet of the compressor, which, in the case of the Concorde, flying a cruise, is 80:1, an incredibly high pressure ratio. The highly efficient GE and X engines, the Boeing 787, only manage 58:1. The Olympus 593's two spools each contained 7 compressor stages, each driven by a single stage turbine. The low pressure and high pressure compressors together provided a pressure ratio of 14:1, a moderately high pressure ratio that would provide moderate efficiency at subsonic speeds. However, the pressure ratio multiplied to 80:1 at cruise as the supersonic air rammed into the unique square inlet engines. This elevated pressure ratio resulted in extreme temperatures inside the engine that necessitated the use of high-temperature alloys that are typically reserved for the turbine blades. Titanium blades were used for the early compressor stages, and high-temperature nickel alloys were used in the even hotter later stages. Cooling the driveshaft bearings became another engineering challenge. Increasing the mass flow rate of cooling oil was not enough to keep the bearings within a safe operating temperature. Looking at the differences between the original Olympus engines used in the Avro Vulcan and the Concorde hints towards some changes the engineers were forced to make. A center bearing located immediately after the high-pressure compressor here no longer exists in the Olympus 593, and the driveshaft preceding it takes a bottle-like shape, increasing in diameter in the new gap between bearings. This center bearing had to be removed because the temperatures were too high in this location directly after the high-pressure compressor. But without the support of the bearing, the driveshaft became too flexible. To accommodate this change, the driveshaft needed to increase in diameter to increase stiffness. The Concorde is full of strange little design details like this, solutions to unique engineering problems caused by the immense cruising speed. In order to decrease fuel consumption as much as possible, the front area of the plane needed to be minimized. Delta wings allow wing spans to be decreased dramatically and reduce the drag created in supersonic flight. However, it creates some issues for low-speed flight, where they struggle to generate enough lift, making takeoffs and landings difficult. This is where the ogival delta wings of the Concorde come into play. This is a form of compound delta wing where there are 2 sections to the wing, with the forward section having a higher sweep angle than the rear section, connected with an OG curve, going from concave to convex curves smoothly. This shape allowed the Concorde to generate additional lift at low speeds through the use of vortex lift.
Oh no.
When flying at high angles of attack, separated airflow would roll over the wings to form 2 stable cone-shaped vortices where airspeeds were high and air pressure was low, effectively creating lift. However, those high angles of attack needed for low speeds created some serious visibility problems for the pilots, whose cockpit would have had a lovely view of the sky if not for the iconic droop snoot. The droop snoot is a one-of-a-kind solution, a mechanized nose that could drop by 12.5 degrees to provide the pilots a clear view of the runway during these high angle of attack maneuvers. The mechanism had 4 positions, controlled by the pilot with this lever. The top position was the fully retracted position used in supersonic flight. The second position lowered a specialized heat shield visor used to protect the cabin windows from the heat of supersonic flight. When placed in this position, the visor hydraulic actuator would retract, causing the visor to retract into the nose fairing. The next position was the 5-degree down position, used for takeoffs and taxis, extending this hydraulic actuator, and the final setting pushes the nose down further into the 12.5 degree setting needed for landings. The plane also had an extendable tail landing gear, which on most takeoffs and landings was not needed, but was present to protect the plane's engines, which would be the first point of contact for what would normally be a tail strike for other airliners. Tail strikes aren't all that uncommon, usually happening on landings in difficult conditions. Some planes, like the 777, also have extendable protection measures in the form of tail skids, as a strike can, at best, force a plane. The airline company. And put the lives of the passengers aboard at risk. In fact, a tail strike is responsible for the crash that claimed the most lives out of any single aviation crash in history. In 1985, a Japan Airlines 747 flight crashed in the mountains of Japan, 7 years after a tail strike had occurred, which had not been correctly repaired. With the high angles of attack demanded by the Concorde for landings, this protection was vital to keep the plane safe. The visor was needed during supersonic flight because the nose of the plane experienced temperatures of around 130 degrees Celsius, while cruising at an altitude of 60,000 feet, where ambient temperatures are usually around minus 56 degrees Celsius. The Concorde went through several design iterations with this forward-facing protection. The earliest prototypes simply removed the lower forward-facing windows completely. But it turned out that pilots like having a view of where they are going, so this wasn't an option for the full production model. However, a version of the droop snoot with a fully metal heat shield was originally considered for the Concorde, which would have eliminated forward visibility during cruise, which was considered non-essential. But thankfully, these heat-resistant glass visors were used in the final version. Working with such high temperature variations between takeoff and landing causes some serious structural issues, especially with the frequency of flights needed to make a commercial plane financially viable. The thermal expansion caused by these temperatures made the plane grow by 20 centimeters on each and every flight. The fatigue this thermal stress could cause would eventually result in catastrophic failure if not properly accounted for. The first issue was finding a material capable of dealing with this heat. Titanium, which was used for the SR-71, could have been used, but due to its cost and weight was ruled out early. Traditional aluminium would not be capable of withstanding these conditions, but a special aluminium alloy, Hindaminium RR58, developed in Britain during World War II for the newly invented gas turbine engines, could. The alloy consists of copper, magnesium, silicon, iron, nickel, and titanium, with the remaining percent being made up of aluminium. Although this material had been developed decades prior to the Concorde, it had never been used in this application. With lower average temperatures than its traditional use inside gas turbine engines, but much longer life requirements, the parts would also be manufactured using different techniques, like the cold-rolled sheets needed for the fuselage. This one process alone affected critical material properties that improved heat resistance. Forged parts tend to have larger crystal grain structures than rolled components, which helps forged components resist the internal crystal structure from creeping when under stress and heat. To adapt this material for the cold-rolled skin of the Concorde, the engineers at Rolls-Royce had to develop new manufacturing methods to maximize the grain size of these cold-rolled components. Manufacturing knowledge that has no doubt been used by Rolls-Royce for modern-day applications. Now that a suitable material had been developed, shaping it in a way that allowed expansion was crucial. Most of this expansion was imperceptible to the crew and passengers of the Concorde. Interior panels could slide past each other to hide the expansion to the passengers, and crucially prevented stress forming as a result of uneven expansion between the hot exterior and cool interior. Wiring around the plane was given slack to prevent the wiring from snapping as the plane expanded, and many components around the plane were corrugated, meaning parts were given a curved shape. This allowed these parts to stretch and flatten the curves like a spring. However, one expansion gap was quite obvious to the crew of the Concorde. As the flight approached its cruise speed, a gap between the flight engineer's console and the cockpit bulkhead began to form. A gap large enough to slide your hand inside of. Or, as became tradition for retiring Concordes, the flight engineer's cap would be placed inside the gap as it closed, leaving it permanently wedged. Like the SR-71, this continual expansion and contraction cycle caused some serious issues with fuel tank sealants. In order to deal with the expansion cycles, a sealant needs to be flexible. Even mundane plastic sealants on household windows need this quality to prevent small movements from allowing drafts getting through. The issue is that high temperatures tend to harden sealants over time, and then, as the expansion cycles continue, the sealants begin to crack and allow fuel to spill out. While the temperatures the Concorde experienced were vastly lower than the SR-71, it was still a maintenance issue. The Concorde used a high-temperature sealant called Viton, but even this sealant hardened and cracked over time, and so, approximately every 1,100 flying hours, roughly once a year, the Concorde was forced into maintenance, which could take 3 weeks to complete. Maintaining the Viton seals was one of the many procedures needed. Fuel tanks would be emptied and then vented for 24 hours to allow technicians to climb inside and manually inspect and replace sealant. This was a massive job and often required technicians to work with just touch, as access to tanks 5A and 7A on the outermost part of the wing was impossible. The Concorde had 13 separate fuel tanks in total, taking full advantage of the large amount of interior volume the Delta Wings provided. Without these fuel tanks, capable of holding 119,000 litres of fuel, the Concorde could not have made it across the Atlantic and would have been completely useless. To put that volume into perspective, a typical Boeing 787, the world record holder for longest commercial flight, can hold just 34,000 litres of fuel. These fuel tanks played a vital role in control of the plane too. As speed increases, the center of pressure of a wing, the point through which all lifting force acts, tends to move backwards. This is usually not a significant issue for slower commercial airliners, but the Concorde's center of pressure moved back by as much as 1.8 meters, more than enough to cause significant control issues that would push the plane into a nosedive if not accounted for. Usually, such a shift would be counteracted by the elevator, which could stabilize the aircraft in pitch from changes in the center of pressure. But Concorde did not have a horizontal tail, and adding elevons on the wing big enough to counteract this change would have resulted in high levels of trim drag at such high speeds. So, Concorde engineers instead used the huge tanks they had at their disposal to deal with this issue. As the plane approached Mach 2, fuel would begin to be pumped out of the forward trim tanks and into the rear trim tanks and collector tanks in the wing, moving up to 20 tons of fuel rearwards and shifting the center of gravity backwards to match the shift in center of pressure, keeping the plane balanced without adding any additional drag with control surfaces, an elegant solution using the tools at hand. The Concorde is an icon in the history of aviation. I can't help but feel an odd sense of nostalgia for a plane I never got to fly in. Hundreds of thousands of passengers can see one of the last remaining Concordes while arriving and departing from Heathrow. Nicknamed Alpha Bravo, this Concorde made its last flight a month after the tragic loss of Air France 4590. It was undergoing major interior upgrades when the decision to retire all Concordes was made, stranding the plane there indefinitely. Alpha Bravo has been in limbo ever since, never getting to undergo the planned upgrades to prevent another disaster like Air France 4590 from ever happening again. An unintentional monument to Britain's storied history in aviation. Accidental monuments like this are scattered all across Britain. Gigantic, no longer functional radar towers can be found all over Britain. These towers were among the first radar systems ever constructed and played a vital role in the defense of Britain during the Battle of Britain, a system that the Germans vastly underestimated, thanks to not just the technology, but the logistical and strategic systems that supported them. This is the story of our latest episode of our Battle of Britain series that delves deep into how Britain's radar systems worked and how those systems were integrated into an effective intelligence system. You can get access to the entire Battle of Britain series and our Logistics of D-Day series by signing up to the Curiosity Stream and Nebula bundle deal for a little over $1 a month. With this yearly subscription to Curiosity Stream, you can enjoy the mountain of award-winning documentaries on Curiosity Stream and support independent content creators like me over on Nebula. This is the best way to support this channel. Nebula gives us a place to experiment in safety, without any worries of alienating our current audience on YouTube or being demonetized for covering sensitive topics like war or tragic disasters. Your support there has helped this channel evolve and grow, and we are able to give you exclusive content like this as our thanks. You can sign up to this amazing deal by clicking on this button on screen right now, or if you're looking for something else to watch right now,
Hey, we're done, Abby. Cool. You know what? Give me a second here. Okay, starting over. We are gonna watch a different video. This we learn about how the Concorde was built. Now we're going to learn why the Concorde was taken down. Because actually might be fun to learn. I've actually never got to. I do know why, but you know, it's fun to learn. Yeah, we got some time before we have to switch. Alright, let's do the real story.
Hey, Dr. Drew, my wife Susan here.
I'm just, alright. That works. Play capture. Over. Give me a second here.
It took 121 seconds. A more than 30-year-long, almost spotless safety record erased within minutes as the Aerospaziale BAC Concorde crashed into a hotel just west of Charles de Gaulle Airport in Paris. But what exactly happened, and during the time leading up to the flight? Using the final report, I will now tell you the story of the beginning of the end of the Concorde. Stay tuned.
Okay.
A huge thank you to Curiosity Stream for sponsoring this video. Air France flight 4590 was actually a charter flight. It was scheduled to fly from Charles de Gaulle Airport in Paris, France, over towards JFK International in New York, United States. Once they landed in New York, the passengers, who were mainly German but other nationalities as well, were supposed to get onto a cruise ship that would take them down to Ecuador in South America, making this probably a one-in-a-lifetime trip. There was 100 passengers scheduled for the flight, and 6 cabin crew and 3 pilots. The aircraft being flown was the legendary Aerospaziale BAC Concorde, one of the most beautiful aircraft ever constructed and a feat of engineering. The Concorde first flew on the 2nd of March 1969, and during its more than 30-year tenure, it had never suffered a fatal accident. There are a couple of things that you need to understand technically about the Concorde in order for this story to make sense. If we start with the wing design, we've all seen these beautiful pictures of the Concorde flying with their fantastic delta wing. Now, the reason that the engineers used a delta wing for the Concorde is because a delta wing will work well both in the subsonic, transonic and supersonic speed ranges. The issue with the delta wing though is that in order for it to provide enough lift for takeoff and landing, you need to have both a very high speed and also a quite high angle of attack. Just to give you an example, a Boeing 737 would generally take off at a speed of around 140 to 150 knots. The Concorde, on the other hand, needed about 200 knots. And this is really important because those type of speeds would put an enormous stress on the tires being used on the aircraft. In fact, the Concorde, during its 30 years of operation, had 57 tire bursts. 12 of those had caused structural issues with the aircraft as pieces of tire had been thrown up towards the underside of the wing. And in 6 cases, the wing tanks had actually been penetrated. The most serious of those incidents happened back in 1979, where a Concorde taking off from Washington in the United States had a tire burst during takeoff. Pieces of the tire penetrated the lower part of the wing and one of the wing tanks, causing a small fuel leak. And also it brought damages to the hydraulic system, making it impossible to retract the gear. After that incident, a major investigation was launched into the airworthiness of the Concorde, and a lot of recommendations were made, mainly towards strengthening of the tires being used and the protection of the hydraulic systems in the landing gear. But there was also some evaluations about the risk of fire. But the investigation team felt that the amount of fuel that could escape from a fuel leak caused by tire debris was relatively small, and hence the risk of fire was very small as well. Another thing that you need to understand about the Concorde is that it has a quite complicated fuel system consisting of 13 tanks, 12 of which is housed in the wings and the body of the aircraft, and a 13th tank that is situated towards the very back of the body. And that tank is used as a trim tank where the pilots can transfer fuel into or out of depending on where they want the center of gravity of the aircraft to be, which is really important, especially during takeoff. The engines on the Concorde were 4 Olympus twin-spool turbojet engines that were situated towards the back of the delta wing, just outside and slightly behind the main landing gear. They had variable air intakes in order to be able to fly in supersonic flight, and they also had secondary air intakes on the lower side, slightly behind the main air intakes, and those air intakes are actually going to play a quite important role in this story. All of the 4 engines also were equipped with full reheat or afterburner capability, giving the aircraft a further 18% of thrust during the takeoff. The flight departed on the 25th of July 2000, and already from the start there were some problems. Originally, another Concorde was scheduled to do the flight, but they changed over to this individual during the night. And when the dispatcher started doing the planning for the flight, he realized that there was a technical issue with this Concorde, specifically to one of the thrust reversers. Now, it was not a problem that would keep the aircraft on the ground, but it had a performance penalty, and that performance penalty would potentially lead to a need for a fuel stop en route. On top of that, most of the passengers were German citizens, and they had flown in from Germany earlier. And there had been some kind of problem in the Air France system when it came to checking in both the passengers and the bags. So a lot of the passengers and the bag were actually not on the passenger manifest when the dispatcher started to do the load sheet. He went with this information to the flight crew when they arrived, and the flight crew said that they would take care of the flight planning from that point. The way they did this was they contacted the engineering department at Air France, asked them if they could possibly fix the thrust reverser. They got a positive response on that, and then they proceeded with the pre-flight. Eventually, the passenger discrepancy was thought to be fixed, but they ended up with 19 more bags on board than what the load manifest would show, giving them a little bit more weight. Around 1400 UTC, so that's 1600 local time in Paris, the flight crew started to do their pre-flight inspections inside of the cockpit. Now, the crew flying consisted of a captain. It was a 54-year-old male with 13,477 hours of total time, of which 317 was flown on the Concorde. The captain was scheduled to be the pilot flying for this flight, and the pilot monitoring was going to be the first officer. He was a 50-year-old male with 10,035 hours and 2,698 hours on the Concorde, and he was also a simulator instructor on the Concorde. Joining them on the flight deck was also a very experienced flight engineer. He was 58 years old, a male, with 12,532 hours of total time and 937 hours on the Concorde. So this was a very experienced flight crew, which was typical for the Air France Concorde crews, which was a very tight little group consisting of only about 30 pilots. As the flight crew starts preparing the aircraft for flight, the engineer comes back up to them, informing the captain that the thrust reverser is now fully functional, which means that they can upload as much fuel as they need in order to fly directly toward New York. And they settle on a final fuel figure of 95 tons. The crew starts discussing that this is going to bring the aircraft up to a weight which is very close to their maximum structural weight for departure. And when they do the calculation of their performance figures, they settle on a V1 speed of 150 knots, a V rotation speed of 198 knots, and a V2, which is the engine out speed of 220 knots. The dispatcher comes in with the final figures for departure, and he tells the crew that he has calculated on a taxi fuel burn of about 2 tons. This is later going to turn out to be way too much, but we'll get to that in a second. At time 14:25, everything is ready for departure. The cabin crew has given cabin secure, all of the passengers are seating down, and the flight crew receives their startup clearance. They start up the Concorde engines in sequence 3, 2, and then 4 and 1. And once the startup sequence is complete, they ask for taxi clearance. The runway used on this day is runway 26 right, which is one of the longest runways in Charles de Gaulle. So the air traffic controller asks the Concorde if they are able to take an intersection takeoff. But given their very high weight, the captain instead asks to get full-length departure, runway 26 right. They receive their taxi clearance to start taxiing down taxiway Romeo to holding point, runway 26 right, and at time 14:35 UTC, the aircraft starts moving down towards the holding point. As they're taxiing out now, the crew continues with their pre-departure preparation. As part of that, the first officer realizes that one of the electrical control systems for the rudder keeps jumping out of its primary control system into its backup control system. He comments this to the flight engineer. He says, "Hey, you got the indicators going into green all the time." And the flight engineer responds back to that, yeah, that's true. They discussed this a little bit. They decide to go back into the primary control system anyway. And the flight engineer says that if this problem continues or happens during the takeoff roll, well then we'll just ignore it, because this is a dispatchable fault and it's not going to have any impact on the flight. During this taxi out as well, about 4 minutes prior to departure, they initiate a fuel transfer from fuel tank 11, which is at the very back of the aircraft, towards the feeder tanks in order to get the center of gravity of the aircraft to 54%, which is the sweet spot for takeoff at maximum takeoff weight. This fuel transfer was successfully completed a few minutes prior to departure. At the same time as this is happening, a DC-10 from Continental Airlines is lining up and taking off runway 26 right, the same runway that the Concorde is just about to take off from. During the takeoff roll, a short metal strip about 43 centimeters falls off the right-hand engine of the DC-10. There are no indications in the cockpit about this, there's no warnings, and the crew just continues to fly towards the destination. Because this happens only a few minutes prior to the Concorde departure, there are no runway inspections that could have picked this up. In fact, in France at the time, there was only mandated 2 runway inspections per day. The Concorde is now taxiing and getting closer to the holding position on Romeo for runway 26 right, and the captain does a takeoff briefing. Now this is something that we always tend to do, where we do a little bit of a quick summary of the most important points before we depart. And the captain says, so the takeoff is at maximum takeoff weight, 180 tons 100, which means 4 reheats with maximum N2 of 103 and a failure N2 of 98%. Between 0 and 100 knots, I stop for any oral warning and the tire flash. And the tire flash and the call out is coming from you, right? Between 100 knots and V1, I ignore the gong, I stop for an engine fire, a tire flash and a failure call out. After V1, we will continue on the standard instrument departure, as we just talked about, and will land back on runway 26 right. So this is a pretty standard takeoff briefing from a captain. It outlines what the crew are expected to do in case of a rejected takeoff in the low speed regime, which in this case in the Concorde is between 0 knots and 100 knots. They basically stop for anything. The gong that they're referring to is what would be equivalent to a master caution warning in a Boeing. It's just a oral warning that some kind of failure has occurred. It might not be a critical failure. And then from 100 knots up to V1, they're a little bit more restrictive because they're now in the high-speed regime of the takeoff. So from that point, they only stop for engine fire warning, failure warning, and in this case also what they call a tire flash. A tire flash is a warning light that comes on if the system feels a sudden loss of pressure in one of the tires. Now, in the Boeing that I fly, we do not stop for a burst tire above 80 knots. But in the Concorde's case, it has proven to be a much bigger problem, so it's included in one of those critical failures that they will stop for in the high-speed regime. And above V1, they are committed to the takeoff. So all pilots are trained that after V1, if you would reject at that point, you will do a potentially catastrophic runway excursion. So instead, we bring the aircraft into the air, sort out any problem, and in this case, they're discussing coming back to land at a very long runway 26 right again in Paris. But as we're about to learn, the failure that these pilots are about to experience is going to be much more complicated than that. The captain now also asks the flight engineer how much fuel they've used during the taxi, because remember, in the load sheet they had 2 tons calculated. The flight engineer responds with, we've got 800 kilos there. So this would indicate that they're actually using about a ton less of taxi fuel. And since they were already at the maximum takeoff weight, using the 2 ton of taxi fuel that they were supposed to use, if they've used a ton less, it means that they're now about 800 kilos above maximum takeoff weight. The flight engineer at this point also says, brake temperature is checked at 150. And the captain asks, is it hotter on the left or the right side? The flight engineer says that it's about the same. And that's going to turn out to be a really important statement for the investigation later on. At time 1442 UTC, the Concorde was clear to line up and clear for takeoff from a 26 right. Air traffic control gave them the surface wind of 090 degrees at 8 knots, and the pilot had not calculated with that much tailwind in their performance calculations. If they would have seen that their maximum takeoff weight had now been reduced to 180 tons rather than just above 185 tons. The limiting factor here would have been the Concorde's tire speed, because if you take off with tailwind, it's going to bring you up into a higher ground speed before you get enough airspeed to rotate the aircraft. And in this case, the tire speed would have been too high. The later investigation would show that this didn't have a real impact on what happened to this flight. And I also kind of understand it, being a pilot myself. When you line up, there's a lot of things that's happening at the same time. And if you suddenly get a different wind than what you've calculated for, it's easy to miss that, right? But if you're a pilot out there, it is really important actually to take the time and to really think about the wind that you're getting before you start your takeoff roll. From this point onwards, things are going to happen really, really quickly. And this is where the 121 seconds start. At time 14, 42 and 30 seconds, the captain advances the 4 thrust levels in the cockpit towards takeoff thrust. This causes the 4 mighty Olympus engines to roar into full takeoff thrust with full reheat engaged, and the aircraft starts accelerating down the runway. 24 seconds later, the first officer calls out 100, which is then followed by the flight engineer saying 4 greens. This is indicating that each of the 4 go lights that is associated with each engine is showing that the engine is working normally and that the 4 reheats are engaged. 6 seconds later, the first officer calls out V1, and there's now no return from this takeoff. This is about 35 seconds into this flight. At time 14:43 and 9 seconds, a slight yaw to the left is noted on the flight data recorder. This yaw was not caused by any rudder movement, and at this point, when the aircraft passed about 1,700 meters of the runway, they also found pieces of the water deflector from the left-hand main gear. So this probably represented the time when the Concorde rolled over that metal strip that was left behind by the DC-10 that had departed earlier. Within half a second, noise is recorded on the cockpit voice recorder, and that's likely coming from the explosion of one of the tires on the left main gear buoy.
KFC's $20 fill-up box?
Yeah, I need to know about that. Yeah,
at this point on the runway, they could find the metal strip and also pieces of tire debris. 1 second later, the aircraft has accelerated to a speed of 178 knots. And at this point, that's about 1,810 meters into the takeoff, a change of noise is heard in the cockpit. What has probably happened here is that pieces of the exploded tire have been thrown up towards the underside of the left-hand wing in the area of where fuel tank number 5 is situated. Now those pieces have impacted the wing with such a force that it actually buckled the underside of the wing inwards and the area around that buckle a little bit outwards, causing an enormous pressure wave inside of the tank. And since this tank was at this moment completely full, that pressure wave didn't have anywhere to go except pushing further on the area of the tank next to where this piece impacted, causing a rupture outwards of the fuel tank. And the reason that the investigators think that this is what happened is because they found pieces of the number 5 fuel tanks at this position on the runway. But the pieces indicated that the rupture had happened from inside of the fuel tank and not from the outside. The change of noise that can be heard on the voice recorder is most likely coming from the fact that several dozens liters of fuel is now gushing out through this hole from the number 5 fuel tank. And it has gotten into contact with something that caused it to ignite. What caused the fire to ignite and actually sustain itself is something that was greatly discussed in the subsequent investigation as well. But most likely, the tire, when it exploded, caused a breakage of some electrical wires in the left gear strut. Now, those broken wires then caused arcing that ignited the flame, and the fact that the landing gear was still extended meant that behind the landing gear there was a turbulence zone that allowed the flame to stabilize and maintain itself without being blown out by the airstream. What happens now is that the aircraft starts veering towards the left of the runway. The captain counteracts with right rudder to maintain the descent line, and this is not because the engines are starting to fail, at least not at this point. Instead, it is likely that this veering moment is coming from the damage made to the left-hand tires and also because of the aerodynamic drag that the flame is producing behind the aircraft. 2 seconds later, the aircraft is starting to lose thrust on both engine number 1 and 2, so both engines on the left-hand side. In the case of the number 1 engine, it's because it's ingesting a lot of debris from the broken tires, so rubber, things like that, and also quite a bit of hot gases. And in the case of engine number 2, which is the engine that's closest to the landing gear, it is because of ingestion of hot gases. As an engine ingests these gases, it changes the pressure inside of the compressor, and it can lead to compressor stalls, which is what's happening here. So the engine is basically choking on the gases. The first officer now calls out, "Watch out," quickly followed by the flight engineer calling the exact same thing, "Watch out." And this is likely because the 2 go lights of engine 1 and 2 would have extinguished at this point, as they are stalling and not producing the thrust that they're supposed to do. The aircraft is now at a speed of 187 knots, still 8 knots below the rotation speed. But because both engine 1 and 2 have essentially failed at this point, engine number 1 is slowly recovering, but engine number 2 is back in idle thrust. The aircraft is starting to yaw very, very hard towards the left. The captain is counteracting this, but the aircraft is still starting to slightly veer off the center line. We don't know why the captain decides to start rotating at this point. Maybe it is because he feels that he's about to exit the runway. Maybe it is to avoid other traffic that he sees further down on the taxiway. We don't know this. But the fact is that he does start to rotate the aircraft, and he rotates slower than he would normally, probably indicating that he's aware that the speed is not high enough. As the aircraft is rotating, the flight engineer calls out something that sounds like "stop," but it wasn't clear on the voice recorder. But only a second later, he calls out "engine failure, engine number 2." And he's calling only engine failure on engine number 2 because engine number 1 is actually starting to recover from those initial stalls. But as the aircraft continues to rotate and the angle of the nose comes up higher and higher, the airflow changes around the wings, probably causing these hot gases once again to be ingested into both engine number 1 and engine number 2, probably using those secondary engine inlets that we talked about before, and this causes further stalls, which once again reduces the thrust back to near idle on both of these engines. At this point, the first engine fire alarm also can be heard in the cockpit, and the flight engineer responds to that with calling "shut down engine number 2," and the captain responds with "engine fire procedure." As this is happening, the air traffic controller can see this all happening out from his viewpoint of the control tower, and he calls out, "Air France 4590, you have flames trailing behind you." The first officer reads this back. The flight engineer is now doing the engine fire procedure, which means that he is reducing the thrust lever back to idle on engine number 2, and he is also pulling and rotating the engine fire handle. This momentarily removes the fire alarm, as the extinguisher is likely cooling down the engine, but it's soon coming back again because of the fact that the fire is not actually in the engine, it's outside, and the engine fire circuit is just feeling the increase in temperature from the immense fire that is burning outside. While this is happening, and remember, everything that we've covered so far has only taken a few seconds, there's another radio call from an unknown aircraft somewhere on the airport. And the pilot there says on the radio, "It's really burning, eh? And it's burning, and I'm not sure it's coming from the engine," which is going to be very helpful evidence later on to the investigators. The Concorde is now finally airborne, and just before it became airborne, it ran over a few edge lights on the left-hand side of the runway. And the crew now faces the next problem, which is their airspeed. Because they rotated at a slightly lower speed than they normally should have rotated with, they're now maintaining a speed of 200 knots, while their engine out climb speed is 220. This means that with that airspeed, they won't be able to climb or even maintain altitude. And the first officer points it out by calling "speed, speed" several times. Engine number 1 is now recovering slightly, but it's heavily damaged and will never get back up to full thrust again. Engine number 2 has been shut down through the engine fire procedure that the flight engineer had just completed. And engine number 3 and 4 has gone into something called a contingency mode, which is where they are producing as much thrust as they possibly can in order to counteract the loss of thrust on one or two of the other engines. The Concorde is at an altitude of 100 feet radio with a speed of 200 knots, and they're climbing with about 750 feet per minute. And at this point, air traffic control calls them and says, "Air France 4590, you have large flames trailing behind you, and you have priority to return back to the airfield." The first officer reads this back, and as he's done so, the flight engineer reminds him to take the gear up. Now, the first officer responds initially no to that, and that's likely because he knows that as a procedure, if there's an indication of a damage to the landing gear, the Concorde is not supposed to retract the gear. But then the captain breaks in and gives a direct order to retract the gear. The first officer tries, but it is evident from the cockpit voice recorder that he is unable to do so. He just cannot seem to get the gear up. The reason for this is likely because of the damage that has been caused by the tire explosion. It might have damaged the landing gear door on the left-hand side, and because of the sequence that the landing gear retraction is supposed to follow, if the landing gear door does not move when it's being commanded to do so, the landing gear will stay out. The captain now turns over to the flight engineer and asks him, "Are you shutting down engine number 2?" And the flight engineer responds with, "Yes, it is shut down." The first officer again calls out, "Airspeed, speed," and then, "The gear is not retracting." At time 14, 43 and 55 seconds, the first indications of an uncommanded roll can be seen on the flight data recorder. This roll likely is caused by the fact that the fire has now been burning for a while and it's starting to melt the inboard elevon on the left-hand side, which is causing flight control problems. Now the captain is trying to counteract this roll, and meanwhile that is happening, the nose of the aircraft is pitching up more and more, and its angle of attack is constantly increasing. The first officer is listening out to the ATC frequency, and he can hear how Charles de Gaulle Tower is talking to the fire leader, who is telling the fire leader that the Concorde is likely going to return back for straight-in landing on the opposite runway. In response to that, he calls out, Le Bourget, and we are going to try for Le Bourget." The engine fire alarm is now back again in the cockpit, and the engine number 1 is surging once again, removing all of the remaining thrust on that side of the aircraft. This further causes the aircraft to roll over to the left, and it gets into, at the worst point, a roll angle of 113 degrees to the left. The GPWS warning system is now sounding in the cockpit as well, saying whoop whoop, pull up, and as that is happening, there is indications that the thrust is being moved back on the remaining engines, 3 and 4. This is likely to try to counteract the roll and get the aircraft over to wings level in order to be able to get it to continue to fly. Unfortunately, it is just too late. Only seconds later, at time 14:44 and 31 seconds, the Concorde crashes into a hotel in Gonesse, just west of Charles de Gaulle Airport. As it does so, all 109 people on board the Concorde perishes, together with 4 people in the hotel on the ground.
This is terrible time for ad.
The region is still coming to terms with the catastrophe in the system of Turner, with
Alright. Got the video back. Here's one last time for the normal start set. There. Oh, for Concorde.
This was an unspeakable tragedy, and start on the air accident investigation started immediately at the crash site. When the investigators started to go through all of the pieces that was left behind the crash, they very quickly found the left landing gear bogie. And when they examined the landing gear bogie, they realized that there was a crucial spacer missing. The function of that spacer was to keep the alignment of the tires on the landing gear bogie, and without that spacer in place, the bogie could actually start to wobble up to 3 degrees in any direction. Now, could that have actually had an impact on the accident sequence? And also, was there anything that the pilots could have done in order to avoid this accident from happening? I'm going to tell you all about what the accident investigation team found out just after this short
There it is.
that the air accident investigation team started doing when they found out about the missing spacer was trying to find it, because maybe it was somewhere on the crash site. But quite quickly they actually found the spacer in an Air France workshop where the Concorde had undergone some maintenance to that landing gear bogie just a few days earlier. This was a very serious lapse on behalf of Air France, and the investigation team now needed to understand whether or not this missing spacer could have actually caused or aggravated the accident. And the way they went about doing this was they had a look at the performance data of the Concorde. If the landing gear bogie would have started to skew during the takeoff run, or indeed during the taxi out, you would be able to see that on the way that the aircraft accelerated during the takeoff. And also remember how the crew talked about the brake temperature before the takeoff and the fact that it was equal on both sides. Well, that was the first real clue that the landing gear bogie was actually lined well, at least during the taxi out, because if it would have been skewed, that would have had an indication on the brake temperatures, potentially higher on the left-hand side. During the takeoff roll, the investigators had a look at the rudder pedal movement of the pilots to see if there had been some kind of pull towards either direction. But they found nothing. And on top of that, the data from the performance manual of the Concorde very closely matched the actual performance of the aircraft during the takeoff roll. And that would indicate that at least during the takeoff roll initially, before they ran over the metal strip, there was no extra drag coming from the left wheel boogie. So the alignment seems to have been good all the way up until the aircraft crossed over that metal strip and the tire exploded. Together, these data indicate that even though the missing spacer was a major lapse on behalf of Air France, it still didn't have any real impact on the accident sequence. The investigation team now turned their eyes towards Continental Airlines and the DC-10 from which the metal strip had fallen. And when they visited Continental Airlines and they went through the maintenance history of this DC-10, they recognized that this support metal strip had actually been replaced not once but twice within the previous 2 months. And when they looked at it, they realized that the metal strip in itself had not been manufactured according to the engine manufacturer instructions. It had also been drilled 37 times rather than the 12 times that was stipulated by the engine manufacturer. And the metal strip next to it was actually a little bit too long. And that was what was causing this metal strip to be constantly worn down, and probably also the reason that it fell off in the first place. These findings led to quite a lot of litigation and legal issues between the French authorities and Continental Airlines, but we're not going to get into that in this video. Instead, let's have a look at how the pilots performed during these 121 seconds. The Air Accident Investigation team very quickly realized that the pilots had never been trained for a scenario like this, where they would lose both engines on one side together with a huge fuel leak and on top of that a fire. Since the aircraft had accelerated past their decision speed of V1 when they ran over the metal strip and the tire exploded, the crew was essentially committed to the takeoff from that point. If they would have decided to reject the takeoff, it is highly likely that the aircraft would have had a high-speed runway overrun, which would have led to a landing gear collapse, and that together with the already burning fire would have in all probability led to a complete loss of the aircraft. So the fact that they continued the takeoff and brought the aircraft into the air was completely understandable. Once they were in the air, they effectively lacked enough thrust to get the aircraft to accelerate up to any sustainable climb speed or climb, given that they couldn't retract the gear. And the fact that they couldn't retract the gear was probably what was maintaining the flame outside as well. So even if the pilots would have been able to keep the aircraft wings level and airborne, the sustained fire would have eventually started to eat through both the flight controls on the left-hand side and the aircraft structure, leading to the disaster. So effectively, the investigators said that there was very little to nothing that this crew could have done differently in order to avoid this accident from happening. So in the end, the Air Accident Investigation team concluded that a single burst tire, something that had happened to the Concorde before many times and was likely to potentially happen again, was the cause of this catastrophic and unreversible tragedy. And because of that conclusion, the airworthiness certificate of the Concorde was almost immediately withdrawn until some serious improvements could be done to the structure. These improvements included things like Kevlar lining inside of the fuel tanks to make sure that even if a tire would burst, it wouldn't have these catastrophic consequences. It also included the protection and partial rewiring of electrical wiring inside of the landing gear strut and the wheel well bay. And on top of that, the aircraft needed to be fitted with new burst-resistant NCG Michelin tires, and there were also some other minor improvements that needed to be done to the aircraft. All of this led to the Concorde being grounded for more than a year, and just before it was scheduled to get back into service, the horrible terrorist attacks of 9/11 happened in New York. That had a huge influence on the aviation business worldwide, so it was to become the beginning of the end of the Concorde era. The Concorde continued to fly for another approximately 2 years until British Airways, as the last remaining operator, retired the last Concorde on the 24th of October 2003, marking the end, at least for now, for passenger supersonic flight. I also want to mention here that the UK Air Accident Investigation team had some serious issues with the way that they had been treated by the French investigation team in this effort. The UK team said that they had been denied access to crucial bits and parts of the information. They hadn't been able to investigate some of the debris that was found on the runway until much, much later, and many other points like this. And this is all outlined in an appendix to the final report. Now, if you guys want to see an absolutely hair-raising story about two pilots who pushed their aircraft to its absolute limits during a positioning flights in the US, which had some really serious consequences, well then check out this video up here. Or you can binge watch this entire video series about.
Alright, that was the end of that video. I hope you guys like the videos I just showed. We have officially started our descent into, I did Tahiti, so we are starting everything here now. 14. Alright. For those of you that are watching, hello, welcome. Welcome on board this flight. We are descending down to Tahiti right now. This plane knows how to descend fast. Jeez, they didn't even map us. Yeah, it's just gone. Alright, you know, things to do before everything. Never reached 350. Cool. Oh, the industry is open up now as well. Okay. Trying to do something right now. I don't know what's doing. Alright, let's take over 1 to 100. All that. Good. We are almost down to our cruising. Altitude. Okay, yeah. Almost down. Don't forget, guys, to like and follow for the stream. And I just realized that I should get rid of this display captures. We don't need it. Yes. Cool. $41 nautical until the top. $41 nautical until the airport. And we're coming in hot. There's Tahiti, our Barbara right there. Ladies and gentlemen, hold on. Yes, we have Ortho. Yes. Okay, everybody, welcome to Tahiti. That's the island we're headed to. And then, in a couple, tomorrow, we'll be headed to the left and heading to Bora Bora. I can show you on the map. Here's Tahiti, and then Bora Bora. And there, we'll be here somewhere. We'll get there. But that's Tahiti. We're close. No, 17,000 feet, what's it? Let's actually review the weather. Sky, over. Okay, so, we're not gonna look for the weather. I'm looking at Tahiti. We're 4021, so we're going to blown right down, 84 degrees, 10 to mild, 10 visibility, partly cloudy, and it's 298. And we're gonna go down 300. 100%. Wait. How about that? How's that work? I think that's much better. Let me look. Realize we have an echo. Alright, yeah, that works. 8,000 feet. We're down 280 feet. Yeah, cool. Alright, cool. Here's the island of Tahiti. This is gonna be a fun run. There's the airport. Let me get here to X cloud. Wait up, alright. There we go. Cool. Welcome to Tahiti. We're gonna strip trip. And we're gonna go down to the and 250 on 240 on the speed. There we go. There we go. Wow. I'll go to the island. There we go. That's the airport right there. Cool. $240. Yeah. Right. Oh, look here. Oh, yeah, cool. DHT. Miles. That's about clearing out. Alright. Yep. You're perfectly on track. There's we start That's not bad. And what do you do, Marky?
They will shift to landing.
Cool. Now that we got that out of the way, let's do this. This. Check. Asterisk. Check. Asterisk. Oh yeah. Fuel. I don't want to put the fuel right now. There we go. Alright, buckle up. This is gonna be a really rough landing, I'd say. Really rough. Don't ask how rough it is. Really rough. Anyway, we're gonna have to check it out. Come on now. Once we're about zero 39. Let's go to it. There we go. Wait. Yeah, that does look like Tahiti. Island. That's actually good. Alright, I'm gonna capture the planet just slow. I'll make sure we're flying on the road. There we go. We're good. There are 6 minutes left. From that. What's that? Oh, and let's reduce our speed. 160. We are. Nice. Alright, now it's just trying to follow them. Come on. Alright, now that we got that live, Whoa. What is happening? Whoa. Fly. Up here.
Caution. Fuel status. 10 tons. Equals to level. Gear coming down. Autopilot off.
There we go. Oh. Alright.
Gear down. Greens.
Thank you. Command of control. Very delicate work. Alright. Backline stuff. There we go. Welcome to Bar. Let's hope for the best landing. Alright. Fire reverses don't work, then that might be an issue. Oh there. Let it steady. Nice. Still. All together. There we go. There we go.
500 feet.
Check.
400. 300 feet. 200.
Check.
Turn throttle off. 100. 30. 40. 20. Contact. Listening.
Actually, not bad about that. Ladies and gentlemen, welcome to Bora Bora. Well, Tahiti. Welcome to Bora Bora. That was actually a really good landing. I'm actually kind of surprised I was able to pull that off. Alright, let's get to the stand. And water bar does look beautiful. But the itself does look beautiful. Now we're back to alright. Oh, look at that. I'm not done with that, but look at this. Oh, look. You gotta love it. Alright. Now the lights comes off, text lights. On ground. Oh, sorry, I'm my phone texting. Alright. Let's just find our gate. Nice. Yeah. Our gate. And this one. That's our channel right up there. Well guys, I do hope you guys love this, well, enjoy the flight. While we did Tahiti to bar to Tahiti. We might take the Q400 or the Challenger, I don't know, but you'll probably see the live stream pop up tomorrow. And I'm gonna get myself some lunch, probably, and I'll do a replay, do shutdown, and stuff like that, and then we'll call it a day today. Flights now. Hold on, yeah, we'll take Toronto to get to. I'll show you guys how it works. I don't want to park on and yeah, we'll do replay of landing, and then we'll probably set up the entire plane and call it a day here. Get some lunch. Yeah. Yeah. Out of the engines. Park brake. And let's do this one last time. Let's look at the landing. Wow, I was really doing a lot of technical. See what it looks like from the outside. That's what I want. Yeah, you're good. Close. Not bad. Not all. That was probably one of my better landings. Let's do this view. Actually, yeah. Let's look at the view. That is much better. And I will do a view of the island too, but let's look what it looks like from the passenger side. That's all. And looks like Long Island. Okay. Alright. I'm gonna leave you guys with one more view, which is an iconic runway view real quickly. Yeah, we'll do that view. And then I'm gonna go eat dinner, lunch, and we'll call it a day. Thanks for uh, thanks for all that came and watched, and thanks for being here. And well, I hope you guys have a wonderful weekend. We'll be back tomorrow for Bora Bora. So enjoy that. Yeah, that's all I have to say. Cool. Oh, and we'll probably get some Microsoft Flight Sim 2020 action happening in 2 weeks or next week. It depends. But that's all I have to say for now. Let's get some music in here. Cool. See you guys.